All right, hi everybody, and welcome to the first lesson of Mark Paulson's Brown School. I hope you're all enjoying the sunshine. I'm in here at Flight Lab, just studying away and making this lesson plan. So today we're going to be talking about hovering flight, and this is one of the more interesting lessons for me because I had a really hard time learning to hover. It took me probably 8 hours, I would say, of practice, like doing other things and coming back to it and going over it again. So kind of getting a good impression or knowledge base for how the helicopter hovers, why it hovers, what happens while it's hovering. It's a good thing, I think, to kind of solidify that skill. So things we're going to talk about today, just the forces acting on the helicopter when it is hovering, coning is one of the effects of basically just weight and lift, and we're going to talk about how that works. Translating tendency as well, and how it's counteracted. Ground effect is one of the things that we try to utilize as much as possible in hovering flight. And then loss of tail rotor effectiveness, which is interesting. It has nothing to do with mechanical failure or anything like that. It's just strictly aerodynamic. So we're going to talk about that a little bit. So first, let's talk about the forces that are acting on the helicopter. See my excellent little R22 here. So you get your helicopter, and as it sits, right, gravity, weight is forcing on it. As soon as its blade starts to spin, it produces lift, and we lift up, and that's when the forces start to equalize, and that's the principle of hovering, is like all these forces are equal. So that's one of the biggest things to get out of this part of the lesson, is that we have four forces, right? So here we've got lift, and opposing lift is weight, and the next part is thrust, and counteracting thrust is drag. And you also get something called a resultant when you combine all these forces, and that is more for forward flights and that kind of thing. So we'll just leave it at this. So drag is equal to the thrust at a stationary hover, and lift is equal to weight. And that's why we get that sustained, no movement hover. All right, now coning has to do with a few different things. One of them being centrifugal force, and the other one being lift. So I've got my little model helicopter here, which I'll demonstrate here. And what I'm going to do is just lift up on the blades. And you see they bend pretty good. I mean, so that's abnormal coning because while the rotors are spinning, they're producing centrifugal force, which is an outward force on the blades, and it holds them nice in tensions, right? So if I pull out on the blades and lift up at the same time, see the blades still cone just a little bit, right? And that's because the centrifugal force is holding the blades rigid, and then the lift, which is overcoming the weight at this point, that weight is dragging down the blades, which create this cone shape. And so that's basically the principle of coning. It has to do with centrifugal force and lift. And translating tendency, as we learned before, the tail rotor's primary function is to counteract torque. Here, I'll tilt this up a little bit. So as the rotor blades rotate counterclockwise, the aircraft wants to spin in the opposite direction. Tail rotor thrusts produces thrust to counteract that torque, and it also provides enough thrust to actually move the helicopter sideward, in this case to the right, or towards the advancing side, Now, one of the ways that we counteract that, some manufacturers will tilt the mast slightly to counteract that movement. Some manufacturers suggest that you rig the rotor blades individually so that they provide a little bit of tilt, and then others we just have a manual input, basically kind of hold it steady. And ground effect is one of the things that's one of the most important parts of the hover, especially when you get into off airports and all that kind of fun stuff. So basically what you've got here, I'll just leave this helicopter up. With normal hovering flight, you've got this inward flow of air. So it's coming from the top, pushing downward. And that's kind of creates all this downwash, but it all comes from the top for the most part. Now, in out of ground effect hover, what we call OGE, so we've got OGE, out of ground effect hover. It creates these rather large, we call blade tip vortices. And these are areas of disturbed air. This air is being kind of recycled. We have this direction of airflow. Right away. Arrows here. So we got this directional airflow around the blade tips, which basically makes the area across the rotor disc smaller where lift is actually produced. So we're producing essentially less lift, which requires more power, more blade angle, more angle of attack. Now, with the introduction of ground effect, which in this part we call an in-ground effect, however, which we're utilizing that ground effect. These rotor tip vortices actually get a little bit smaller. So we're utilizing more of the rotor disc for lift. And I'll get a little ground here. And this downwash, which in the OGE hover is just going straight down and just getting pushed away, it's actually moving down towards the ground and being blown outward. That creates kind of like a cushion. For one thing, it reduces the blade tip vortices and basically gives us more lift with less power, which is always a good thing, especially when you're hovering at high altitudes. Ground effect isn't perfect though, so one of the things, if we have like tall grass, rocks, boulders, whatever, all that kind of stuff, anything that will disrupt that outflow of air, that's going to reduce the effectiveness of ground effect essentially. So, and then also tail rotor effectiveness. I'm going to kind of breeze through this a little bit. I don't want to spend too much time on it. We're going to talk about it way more in depth later on in the lesson. But there's basically three types of what I want to get across right now. Three types. You got your main rotor disc interference, excuse me. So main rotor disc interference. And what that requires is a left quartering headwind. And basically, those blade tip vortices that we just talked about, those are getting blown into the tail rotor. Right, so those initially cause an increase in tail rotor effectiveness, which is misleading, which is why it's so dangerous to get trapped in this particular form of LTE. And then the next part is called, weathercock stability. Well, actually, we'll go through tail rotor vortex ring state is kind of the next step. Now what this requires is a left crosswind. And essentially, we're blowing remember the downwash we talked about for the main rotor, as that tail rotor is producing thrust, right? Producing thrust to the left. With the left crosswind, we're actually blowing that downwash back into the tail rotor, which creates a more turbulent state as well. And this just has the and the last one is weathercock stability, and this requires a tailwind, right? So we got our tailwind. And that's because the helicopter is designed to be aerodynamically efficient, basically, when the air is hitting the front of the helicopter. So if you turn it around, it's going to be constantly trying to face the direction that it's most happy, which is nose into the wind. All right, so that's where you get that weather bending. Some people call it weather banding as well. If you know what those little roosters on the top of a barn, the same principle applies basically. It's always trying to face into the wind. Right, so the helicopter is basically just trying to face the wind. So I'm going to go through this with the helicopter here as well. Just got to get a better picture of it. So I've got my wind vector pen here. All right, so with the left quartering headwind, right, these disc vortices are getting blown into the tail rotor. And what that does is initially, because there's more air reaching the tail rotor, it initially increases the effectiveness of the tail rotor. So you need end up adding a little bit of right pedal to stay down the runway heading or whatever you're trying to do. And with that little bit of right pedal, if you were to make a right pedal turn at that point, then you would actually introduce yourself to the next phase, which is tail rotor vortex ring state with your left crosswind. Right, so you've got your little dummy of increased tail rotor efficiency. You make that turn, and all of a sudden you get that decrease, like that rapid decrease because of your tail rotor vortex ring state. And then all of a sudden you've got this rapid yaw to the right as well, which then kind of puts you right into the same position to the position of weathercock stability. Right, so you can see how they kind of build off of each other. So if you get stuck in this, or get duped by that increased efficiency of the tail rotor there, then you can just kind of inadvertently end yourself up, and you'll end up in this rapid right yaw. Now, what you want to do to prevent that from happening, one of the ways you can do it is make left pedal turns. I know a lot of places will just automatically have you make left pedal turns wherever you go. That's not really that practical, because it's the whole point of a helicopter is to be able to do kind of whatever you want, but you got to make sure you do it safely. So basically, what you want to do in this case is to reduce your power. If you reduce your power, that yaw rate will stop. You'll be able to control it with left pedal. All right. So that's all I'm going to start with today. So to recap, we kind of covered basically the forces. We got lift equal to weight and drag equal to thrust in a stationary hover. We've got our coning, which is a combination of centrifugal force and lift. And then our translating tendency, which is one of the byproducts of the tail rotor producing thrust to counteract torque. And then we've got loss of tail rotor effectiveness, which we can basically do our best to avoid. That's pretty much the point of that. Especially with winds greater than 5 knots, once you get 10 knots, it just increases your workload. It's a hazard, and it's better off to avoid it. So thank you very much for tuning in, and I'll see you guys next week.